Today I will talk about the widely tunable dual wavelength laser for continuous wave terahertz radiation. Actually, today we are talk about two parts. One part is fiber-based dual wavelength laser-based fiber system, and the other part is the dual mode laser based on semiconductor device. Will give a talk by Dr. Jeon Park. The outline is my talk. As an introduction, I'll talk about the terahertz technology, and then briefly motivation of this work will be presented, and then I'll demonstrate dual wavelength fiber laser for continuous wave terahertz radiation, and preconceived dual wavelength laser will be discussed. Which one is better? Especially the preconceived laser have many applications. I'll briefly discuss about the swift laser applications, and then I'll propose a new concept, the preconceived dual wavelength laser as an optical bit source, and then I'll conclude of my talk. The terahertz radiation sources have many attractive considerable interest recently because of their potential applications to spectroscopy, communications, medical, agricultural, environmental, and food detection and security field. The photomixing method is promising to obtain the CW terahertz radiation. So the combination of a photomixer and an optical bit source is a promising optical source for tunable continuous wave terahertz radiation. The photomixer is fabricated based on indium phosphide. It will be presented by Dr. Jeon Park. And optical bit source is typically composed of two tunable DFB or DBR laser with different wavelengths. And there are so many terahertz applications, such as good transmittance for non-metal and non-polar materials, and identifying molecular fingerprints by analyzing absorption spectra, and also safe frequency sources with low photon energy is possible. You can see the terahertz imaging applications. The terahertz imaging can be used to detect hidden drugs in envelope or other containers like this. There are some illicit drugs. And also you can find the object inside the box or the container, because the terahertz source has good transmittance for non-metals and non-polar materials. And also you can identify the molecular fingerprint by analyzing absorption spectra like this. The terahertz technology is bridging technology between electronics and photonics. The electronics include radio wave, microwave, millimeter wave. The other hand, the photonics includes X-ray, UV, visible, IR. But there is some gaps. It's called by terahertz gap. The terahertz gap is between electronics and photonics. There are the terahertz technology remains to do a lot of work or research. There is two kinds of terahertz generation system. One is the time domain terahertz system, and the other one is the frequency domain terahertz system. In the time domain terahertz system, the femtosecond laser is used as an optical source. There are some advantage and disadvantage. In the time domain terahertz system, the high signal to noise ratio, and it is well developed. However, the disadvantage is like this: the high cost and big size, because the laser system is bulky, and also it requires data acquisition time and fast Fourier transform module. The other hand, in the frequency domain terahertz system, also a high signal to noise ratio and moderate cost and size, it is possible to generate monochromatic and continuous wave. In this case, usually the optical bit beating optical bit source and photon mixer are used. However, the disadvantage is the low temperature of power. And also it requires mechanical alignment. However, these days, all component is pigtailed with fiber, so we don't need any mechanical alignment. Also, in this case, it can build up with compact and portable source. The photon mixer is fabricated in the phosphide-based photonics. This part is developed by will be presented to Dr. Kyung-Hyun Park. Actually, there are some advantages like this. And also, this is device based on this is the principle of the terahertz generation with the dual wavelength laser. Actually, the dual wavelength tunable laser is an optical bit source. This goes to the photoconductive antennas switch. The optical bit source generates the photocurrent. So we can represent the terahertz power like this. And the pink box represents the optical power of two signals, two light. And the blue box represents the induced photocurrent. So we can measure the terahertz power using this equation. Recently, my collaborator, persons, developed the monochromatic dual mode DFB laser. This part will be given a talk by Dr. Kyung-Hyun Park. I'll skip. So this is the motivation of my work. Actually, the dual wavelength laser with a single longitudinal mode have many applications such as microwave generation or millimeter wave generation and fiber optic sensors. Especially dual wavelength open dot fiber lasers is promising for compact and low cost optical bit source and high signal to noise ratio and wide tuning range for continuous wave terahertz radiation. And also, the wavelength shift laser have many applications for optical coherence tomography, optical fiber sensors. So, because it has high-speed scanning and wide scanning bandwidth. In this work, I proposed the wavelength shift, the frequency shift, terahertz generation based on the wavelength shift laser. Actually, there are two distinct characteristics in open dot fiber laser. One is the homogeneous gain broadening, and the other one is the multi-longitudinal mode oscillation. The homogeneous gain broadening causes the gain competition in the open dot fiber. So it should be eliminated to generate dual or multi-wavelengths. There are some solutions to solve this problem, such as cooling the EDF in liquid nitrogen, exploiting the polarization hole burning effect, and using a hybrid gain medium. Also, the multi-longitudinal mode oscillation should be eliminated for practical applications such as the microwave generation, millimeter wave generation. Several methods have reported by using the ultra narrow band bandpass filter, such as the unpumped EDF section. In our approach, we used the Fabry-Ferro laser diode with a micro heater and fiber Bragg ratings to eliminate the homogeneous gain broadening. And also we used the unpumped open dot fiber sections to generate the single longitudinal oscillation. Here is a widely tunable dual wavelength open dot fiber laser schematic diagram. The laser consists of 10-meter long open dot fiber as a gain medium, and 2 isolators for unidirectional operations, and 3 dB fiber coupler, 2 section unpumped open dot fiber, 2 fiber Bragg ratings, and 2 Fabry-Ferro laser diode. Actually, the configuration is almost the alpha type. The ultraviolet fiber laser divided by 2. Actually, the 50% of the light goes to upper side, and the other 50% goes to lower side. And then the fiber Bragg rating is reflected specific wavelength. The reflection center wavelength of the fiber Bragg rating 1 is 1540 nanometer. Fiber Bragg rating FVG 2 is 1546.4 nanometer. The laser goes to this part. Then the 1540 nanometer light goes back to the coupler. Some of light goes to the far field laser diode. Far field laser diode has a lot of the longitudinal mode. Then when the matches with when the reflection wavelength matches with one of the longitudinal modes of the far field laser diode, then FPLD is injection locked. In order to continuously tune, one side of the FPG is bound to the fixture and the other one is fixed on the translator stage. And also the far field laser diode is anti-reflection coated in the front face and high reflection coated in the back face. The far field laser diode is fabricated by Atri in the Kyunghyun Park's group. This shows the optical spectrum of the far field laser diode, the typical optical spectrum of the FPLD. Actually, you can see a lot of the longitudinal mode. The mode spacing is 0.8 nanometer. It corresponds to the 100 gigahertz or 0.1 terahertz. And also, in order to continuous tune, we integrated the micro heater on the far field laser diode. By applying current to the micro heater, then the longitudinal mode can be continuously tuned. However, the intensity gradually decreases. It is due to the thermal effect of the far field laser diode. Usually, I operated under the threshold current. Actually, threshold current is 22 milliampere, but in my experiment, I injected the current of 20 milliampere. Then we can continuously tune the dual wavelength spacing. Actually, there is one wavelength in this system. There is two laser cavity because the one cavity consists of like this, and the other cavity like this. So when we disconnect the far field laser diode, then there is one wavelength experience the gain because of there is the gain competition by the Holborn effect.
So what's the function of those unpumped?
Actually the unpumped EDF, as I told before, in order to operate a single longitudinal mode oscillation, I put the unpumped EDF section. It's satural observer. As a satural observer, I'll discuss about after.
So excuse me.
Yeah.
Is the gain competition here is very serious?
Yes. Actually, gain competition is just one wavelength is raising. So it's both competition.
So you need to adjust the loss between these two FPG very carefully.
Actually, the far field laser diode is injection locked. It's both wavelengths. This wavelength is injection locked from here, and this wavelength is injection locked from here. So there is two wavelengths, dual wavelengths operated. There is no gain competition. However, we disconnected these two FPLD. There is only one wavelength is raising due to the gain competition. So we obtained the tunable dual wavelength laser according to the strength of FVG, fiber Bragg rating. Actually, the public laser diode a lot of longitudinal mode. The mode spacing is 0.8 nanometer, so we just obtained the 0.8 nanometer step. The 3.2 nanometer is corresponds to 0.4 terahertz, and 8.8 nanometer is 1.1 terahertz. In order to finely tune, by applying current to the micro heater on the FPLD, then the longitudinal mode can be continuous tuned. At the time, simultaneously, we have to strain continuously the FPG, because the FPG wavelengths should be matched with the longitudinal mode of the public laser diode. So we can tune finely and continuously dual wavelength fiber laser like this. And also we obtain the side mode suppression ratio, in this case almost 40 dB, but all wavelengths is more than 35 dB. You can see this is 10, 20, 30, 35 dB. So we obtained. And also, in order to operate a single longitudinal mode, we put the unpumped EDF section. Actually, without unpumped EDF section, as you can see, this is RF spectrum. There is a lot of the mode, because the laser cavity length is 25 meter. So there is the first mode, second harmonic, third harmonic, fourth harmonic, a lot of the longitudinal mode. But when we put the unpumped EDFA as a sectional observer, there is no longitudinal mode, because in this case, actually the two mode beating frequency is 400 gigahertz in the case of the 3.2 nanometer apart. But we have only 50 gigahertz RF spectrum analyzer, so we can measure the optical beat frequency in this case. And in order to confirm the possibility of dual wavelength fiber laser, we measure the continuous wave terahertz generation using this experimental setup. The dual wavelength fiber laser as an optical beat source goes to the photo mixer gap through the free space lens system after amplified by EDFA up to 13 dBm. And also the fabricated photon mixer is mounted onto the silicon lens for the terahertz radiation experiment. And also the cryogenic bolometer operating at 4.2 K is used to measure the terahertz emission power. In order to enhance the terahertz signal, we used the locking amp with sinusoidal function generator. Using this experimental setup, we measure the terahertz output power, terahertz signal. This is the continuous tuning of the CW, terahertz radiation. Actually, the dual wavelength fiber laser can be tuned from 0.3 terahertz to 1.1 terahertz. But the above 0.8 terahertz, there is no terahertz output signal, because we cannot distinguish which one terahertz output power or thermal noise. So actually, this part is the thermal noise level. So we just cannot. We just can detect the point up to 0.8 terahertz. But the problem is the terahertz output power. In this case, less than 10 nanowatt. For practical application, it should be more than 50 nanowatt at least. But we believe that if the material processing optimized, then the terahertz output power will be increased more than 50 nanowatt. And the other part is the wavelength swept laser. There are some applications, optical fiber sensors and optical coherence tomography, optical communications. The wavelength swept laser consists of very simple gain medium and optical band pass filter and feedback element. So actually the gain medium has ASE background. Then the optical band pass sweeping fast, then transmission window of filter goes to the short wavelengths to long wavelengths or long wavelengths to short wavelengths. Then the AS background signal is amplified in the transmission window of filter. Especially the Fourier domain mode locked wavelength swept laser is proposed by Dr. Huber, the MIT group. In this case, it's possible high scanning speed, more than 100 kHz, and narrow instantaneous dynamics, and also it has high phase stability. In this system, all wavelength modes are simultaneously active in the resonator at any given time. So, using this Fourier domain mode locking, we can obtain the higher scanning rate. This system is the wideband wavelength swept laser. When I was doing the Professor Chen's group, I developed the wideband wavelength swept laser using two SOA combined parallel system. So in this case, we obtained the more than 130 nanometer 3D scanning bandwidth, and also we obtained the OCT imaging. This is some examples of the wavelength swept laser. This is the 3D band is 138 nanometer, and we measured the OCT imaging. And also another application is the fiber sensor interrogation system using the Fourier domain mode locked wavelength swept laser. There is a lot of the FVG. So we can measure the static response or dynamic response from the fiber broadcasting sensor interrogation. And also another application is the remote fiber broadcasting sensor system. It is a little bit deeper from above system. In this case, there is 4 FVG, lambda 1, lambda 2, lambda 3, lambda 4. So in this system, the laser cavity has 4. The lambda 1 experienced this length, and lambda 2 experienced another more 100 meter single mode fiber. So the lambda 2, lambda 1 and lambda 2 has experienced different lengths. So the round trip time is different. So if we changing the frequency to the far-field laser diode tunable filter, then the operating wavelengths we can change it. So according to the applied frequency to the far-field filter, then only one wavelength we can find, lambda 1. In the case of lambda 1, is the applied frequency is 33.8 kHz. The other hand, lambda 3 case, the frequency is 31.53 kHz. So only one wavelength raising each frequency. So we can find some position. And another example, we proposed the scanning optical bit source using the optical wavelength swept laser. If we use the wavelength swept laser, one wavelength swept laser and one fixed laser, then we can obtain the beating signal from both lasers. One is the fixed, and the other one is the fast wavelength sweep. Then the optical bit source can be high-speed swept. So this is the wavelength swept laser, and we use the tunable laser as a fixed laser. The difference is the wideband pass filter. Actually, without wideband pass filter, the 3D bandwidth is very large.
If you have one fixed and one tunable laser,
Yeah.
You have to keep that phase relation between the two laser.
Actually, you can see next to the data.
Okay.
Actually, the wideband phase filter is narrow band phase. Actually, compared to the scanning band is very narrow. In this case, just 20 nanometer. And also, we can, without the wideband phase filter, the scanning band is more than 100 nanometer. And also, we measure the autocorrelation signal. Then, actually, the sweeping, when the laser is sweeping, we cannot measure the autocorrelation signal, autocorrelation trace. However, if we static voltage applied to the power filter, then the fixed wavelength we can obtain. So, in that case, we measure the autocorrelation, and also we measure the optical spectrum analyzer.
But even you use a wide path input, even you use a wide band path filter, the bandwidth, the lines of a sweeping laser is still much wider than the tunable laser, right?
Actually, the tunable laser is the fixed,
Yes. So
one fixed.
if you use a fixed wavelength,
Yeah.
this line can be much narrower.
Actually, this is very narrow. The one is the problem is the line is must be narrow.
The output of the DP, its wavelength, its line is still depend on the lines of your sweeping laser.
Actually, the efficiency of the target radiation it should be very narrow line. It should be have a very narrow lines. But in this case, just we obtain the 0.1 nanometer line is in the sweeping laser. So this is the optical spectrum of the wavelength swept laser. The 3D bandwidth is more than 130 nanometer. But this is temporal profile. And then we want to the tuning of, let's say, within few terahertz. So we put the filter, wideband filter is almost the 3D bandwidth is 19 nanometer. And this, the right hand peak shows the fixed laser by the tunable laser. Actually, I always fixed. And also, this 19 nanometer is the wavelength swept laser output. In order to measure the autocorrelation trace, when the applied frequency, applied voltage to the power filter is constant, then we obtain the instantaneous, the continuous, static wavelength swept output. So, in this case, the wavelength swept laser is this is tunable laser fixed output, and this is the static, the wavelength swept laser output. The space of two wavelengths is 1.76 nanometer, is corresponds to 0.22 terahertz. And also, if we changing the applied voltage, then we can changing the ranging wavelength. In this case, it's 3.6 nanometer, that corresponds to 0.45 terahertz. And also, we obtain the 1 terahertz. In order to measure the autocorrelation, in this case, the corresponds to 0.22 terahertz, we obtain the autocorrelation trace. This is the 0.22 terahertz beating signal. And also 3.6 nanometer corresponds to 0.45 terahertz. And 7.92 nanometer is corresponds to 0.99 terahertz. In this system, the sweeping bandwidth is 17.3 nanometer. This corresponds to 2.16 terahertz. Actually, the light peak is the fixed laser from the tunable laser, and the blue and light is the sweeping wavelength. Actually, it is difficult to measure the autocorrelation when the laser is sweeping, because when we want to measure the autocorrelation, it must be the fixed. So you just obtain this one is the fixed and the other one is the swept laser. But in future, in this time, we didn't measure the terahertz radiation signal, because we didn't prepare the continuous high-speed scanning terahertz signal generating system not prepared. So we did measure the terahertz radiation signal. However, the possibility we just got the possibility of the frequency swept terahertz radiation signal. So conclude on my talk. So we obtained the widely tunable and stable dual wavelength open-dot fiber laser using the 2 power ferro laser diode and 2 fiber Bragg gratings. And also we obtained the terahertz radiation signal. However, the power is very low. So if we optimize the material, photomixer materials and the processing, then the terahertz output power will be improved more than 50 nanowatt. And also we proposed the frequency swept optical piece source using the wavelength swept laser and another fixed laser. So in this case, the sweeping range is over more 17.3 nanometer, and signal to noise ratio, actually side mode suppression ratio in this case, we obtained 45 dB. Yeah, thanks. And the other part will be given a talk, Dr. Kyung-Hyun Park, so based on the semiconductor device dual mode laser. Yeah.
Before I move to the next one, you have opportunity to ask a question.
First, in the dual wavelength EDF laser, why do you use the LPD LDS? Because I think the LPD also can choose the wavelength.
Yeah.
Why do you use the LDS?
LBS?
Laser diode, FP
FP laser
laser diode.
diode. Actually,
Why do you use it?
yeah, I told you if we don't use the power laser diode, there is a gain competition, because the EDFA characteristics by hole burning effect. So just only one wavelength is raising.
So you mean you use the laser diode for injection?
Yeah, actually, the power laser diode is placed of the self-injection lock.
So the EDF is homogeneous beam medium, but I think in the gap, the wavelength gap is big enough, such as maybe more than 11 nanometers.
The EDF gain medium has 30 nanometer, 1530 to 1560 nanometer.
7 nanometer.
Yeah.
So big. Okay. So the second question is, at the first schedule
Scanning.
you use the FPD to choose the wavelength, and also you use the EDF SA to get a narrow line wavelength.
Yeah.
But at the second part, you use the swirl source.
Yeah.
But I think the swirl source will bring a lot of noise. So how about the performance of the paragraph between the two?
Actually, if we use the two fixed laser, and each laser is very narrow, each laser has very narrow lines. But one problem is the swept source. Actually, nowadays we only just get 0.1 nanometer narrow lines. But if we enhance the terahertz beating efficiency, then must be the more narrow, less than 0.1 some, the very narrow more than, I think it's, actually in this line is there are some mode, but in order to get high efficiency terrestrial signal, must be single longitudinal mode oscillation. But it is very difficult to get single longitudinal using the wavelength swept laser. Must be solved, I think.
It's difficult when we use the third source. It's difficult to get perfect signal.
Actually, yeah.
Okay.
So what's the typical power you can generate?
The terrestrial power or the optical power? Terrestrial power. Actually, in order to the practical application, it should be more than 50 nanowatt. But in our system, when we use the dual wavelength system, the terrestrial power less than 10 nanowatt. It depends on the photon mixer antenna and also the polarization state.
Okay, let's thank you.
준비도 안 하고 있어. 이 다운 이거 내줘. Thank you. So, before starting my talks, I do appreciate Professor Jeon for inviting us. So, my talk is determined just now. So, in the morning, Professor Jeon and Professor Jones would like to join and give another talk. So, this is one of my previous talks. I will give this talk. So, the title of my talk is Tunable Continuous Wave Terrestrial Generation Based on Photonic Devices. This is our research teams. Our research teams consist of 3 different teams. One is the at-risk photonic device team. The other is KRIS, Korea Research Institute and Semi-Standard and Science. And others is Chungnam National University. I will give my talk as follows. In introductions, I would like to talk about our motivation and also describe our beating source and based on semiconductor device and performance of terrestrial generation, and finally summary of my talk. So, this summary of talk also will be given by Professor Jones. That in recently, technology have received considerable attention for various applications. This you can see some imaging, and this is on spectroscopic data. So it has good transmission for non-metal and non-polar materials, and also it can be identifying molecular fingerprint using spectrometers, and it is also safety frequency source. So as you can see in terrestrial gaps between the microwave region and optical regions. We have experienced a lot of change in optical communication industries, especially rapidly growth of access networks and photonic device request high speed, high bandwidth, and low cost operation, and uncooled operation. So we can use the well-developed semiconductor device and also 5 components. So we can realize the integrated photonic devices. So, this is we have a very nice compound semiconductor labs We developed optical components. As you can see, we developed several different active device and passive device. This view graph already you saw shows the most popular broadband terahertz generation schemes. One is TDM and the others is frequency domain terahertz generations. I think in order to realize point-to-point broadband terahertz spectrometers, we should consider small size and cost and real-time data acquisition, so on. So we proposed a novel semiconductor device. We call it the tunable dual mode lasers. So it consists of three sections, the 2 dBr section and 1 phase section. So let me show you how to generate terahertz waves. So when current applied to both DFB sections, it provides stable dual mode when reverse biased to the phase sections. So output powers of antinode of dual mode lasers can generate the carrier in photoconductive, so which can be generated terahertz via carrier acceleration. So terahertz output power depends on a lot of parameters, and in parameter in red box related on laser part and blue ones related on photomixer. So we developed both one, and one is a dual mode laser and as a beating source, and the other is a photomixer, so called down converters. Detailed device structure is shown. We used 2 loss-coupled DFB lasers and also integrate micro heat for wavelength tuning. So and also we adopting all active structures. So we can we can realize the cost-effective beating source because we applied the micro heaters, so we can tuning with the low cost. So this is a photograph of our fabricated device. So you can see some electrode for laser and 2 micro heater for wavelength tuning. So in this case, to realize this device, we use the conventional holographic grating method. This is a basic characteristic of our micro heat DFB laser. It has above side mode separation lasers above 40 dB, and this is the threshold current is around 3 and 9 milliamperes. So one of this device used to realize Professor Jeon's on 5 lasers. This is our first results. This is the tuning list of dual mode lasers. So in this case, we got above 25 dB SMSRs. So when current this is the 1 and 2 denotes the section names. So we current applied the micro heat number 2 on of DFB2. So we applied the power up to 0.07 and one of mode of DFB2 could move the red shift. And so we applied the current micro heat current up to 0.2 microheat. So one of the DFB1 modes move the shift red shift. So we can get the tunable single mode. In this case, not a dual mode, just a single mode in longitudinal modes. So we get tuning schemes. The tuning range is limited. However, so we can get successfully demonstration dual mode operations. So our device need some modifications, like and extend the tuning range and increase the output powers. So we tried several different types of the multi-mode dual mode lasers like this. So first of all, we'd like to extend the tuning range. So to get the tuning range scheme, so we apply the detuned dual mode laser. In this case, we use the E-beam lithographics. As you can see, this is the Bragg conditions. We select the different Bragg wavelengths. And also, we applied the quarter wave shift and dual mode laser. In this case, not loss grating. In this case, we'd like to use the index gratings. This is some other issue. Not okay. This is some difficult to use. This is operation spectrum. This is detuned dual mode lasers. This is a quarter wave shift dual mode laser, and we found DBR and DFB schemes systems. So we get side mode separation rate above 30 dB, and tuning range still extended. So in this case, we get up to 1.15. But in this case, we can get above 20 nanometers. However, in this case, not a continuous mode. So this is we can easily see some DBR models. So we take all of the advantage of this device. So we'd like to using the more extend and more high power device. So we can try using the wide gain as an active material of dual mode lasers, and also integrate the semiconductor optical amplifier of our beating source. And finally, we'd like to use the small compact photonic integrated circuit as a tunable tolerance source. So we are trying to wide band gap. We are trying to get wide bands, and this is one of the samples of our wide mixed multi-complementary peaks. And this is in this case, we did not get wider tuning ranges. However, some performance is very we get very nice performance like this. So we trying and this performance and also an integration of SOA. So I believe that we can get very nice beating source. We investigate the tuning speed of our dual mode lasers. So in this case, this is tuning turn on and cooling times. So we get 2.4 milliseconds for 3 nanometers. So this is very nice performance. And this is John's already show. To generate the tolerance wafers, so we need some down converter, so-called optoelectronic converter. So as I mentioned before, to tolerance output powers depend on the several parameters in photomixer. And this is the most important factors is carrier lifetime. So we are facing big challenges to realize the broadband high performance and photomixer. We should develop the several old processes, so including materials and material characterization and fabrication. In materials, we are trying to get low temperature grown ingot material and ion implantation schemes. As other materials, we finished developing material characterization and fabrication. We have a 2-inch stepper. So this is a photograph of our fabricated 2-inch ingot photomixer, which grown by low temperature grown using some molecular beam epitaxis. This is and also we developed some broadband antenna. This is we used 3 finger structures in the core. This is line is around 0.5 microns, and this is not a broadband. This is a resonance type, and resonance antenna types, which is so-called dual dipole structures. So to realize the small compact photomix module, so we designed all kind of terrace passive component and also fabricated some modules. So we tried some flip chip bonding schemes using some photomixer chips using PCB just in order to get low cost solutions. So we can realize the small compact photomixers. So this is the same of photograph image of our fabricated dual mode. This is optical fiber active welding process, and this is the electric bias cable. So you can see the head equipped by silicon lenses and semi-hemispherical silicon lenses. This is our first result of terrace emission. So you can see this is a resonance curve, and this is a broadband terrace source. In this case, all of terrace generation measured by helium-cooled bolometer. Next, as you know, so in helium-cooled bolometer have high sensitivity, so it can measure below the 10 to the 12 and 10 to the 13. But a lot of people in this field would like to measure the narrow bolometer. So we are trying to get some Go-ray detector and others. Our photomixer, so this is the homodyne detection, not a heterostructure. So we are trying to homodyne, and last month we measured some terrace powers using Go-ray detector, not a helium-cooled bolometer. And unfortunately, I didn't have files in this biography. Summary of my talks, we developed micro-heat integrated dual-mode lasers and micro-heated fiber injected and fiber lasers, and we developed InGas-based photomixers. So in this case, still need much improvement. So in order to use to get wideband photomixers, so we should obtain below the picosecond carrier lifetime. So far we get around several picosecond materials. So I believe this year we can get some below picosecond phenomena. And this is our further works. We can try to semiconductor optical amplifier integrated dual mode lasers and also waveguide type and photomixer. So after that, we can develop the very small, compact, tunable terrace spectrometer. Thank you for your attention.
Question?
So I have a question. So how fast? So what's the tuning speed?
Yes, I already show one view up. And in this case, we experiment the tuning speed. In this, we get 2.4 nanometer per 3 nanometer. So in case of 1.5 also, for tuning of the 1 terahertz, we need 8 nanometer is necessary. Okay, so to control the 8 nanometers, so we just need 6 or 7. That is very short. Faster enough to tuning the spectrometer. As you know, some system shows the more longer skin speed. So in this case, very high speed enough to.
Okay, the speed around
Yeah.
160 or 170.
What's meaning? What?
Okay, that's
Yeah.
Question on the photomixer.
Yeah.
I don't understand why. So the photomixer, essentially you have lights go through the junction.
Yeah.
And they will generate a terahertz.
Yes, sir. Because the in photomixer consists of two parts. So the one is a photoconductive switch. As I mentioned before, photoconductive switch is when enter the optical power, that the resistance is dramatically down. So it can flow the current. So we call it photoconductive. There is and then some of optical power input the photomixer. They generate electron hole. So and on we bias the electron. We bias that photomixer. Some electron hole generates X-ray with the bias. So as you can see, some electromagnetic wave is some when the accelerate the charges, they can generate the electromagnetic wave. So in this case, some small trials wave is generated with the bias. So a lot of people would like to increase the bias. So as you know, in 1.55 system, it's very difficult to get the high bias situation because in-gas band gap of in-gas is very small compared to that of gallium arsenide. As you can see in photonic West, there are a lot of several Taras systems that include gallium arsenide system, not in-gas system. However, a lot of researchers want to develop 1.5 system because we can use a lot of well-developed semiconductor and 5-ways component. But this is a killer. This is the big challenge part. So if we get very nice performance, a lot of people want to that technology. Okay?
Can I see the picture of probe again? Probe tip. So what is the minimum width?
Yeah. Yeah. This is very important. So we got in case of pulse case, we got this one 5-ways IMNA waves, so IMNA pulse waves. In that case, is at problem is 80 femtosecond pulse. In that case, there is no problem. However, so in Professor Jeon's lasers and our dual mode lasers impinged on our photomixer. In this case, a CW case, not a pulse case. There is something problem because a lot of optical power so it's impinged on photomixer. State-of-the-art of photomixer is a conversion efficiency around 10 to the minus 4. So they're making a lot of heating. So this is we can see dramatically degradation. So he got around the nanowatt levels. So we are trying to improve the photomixer. So it's using the high heat spread layer and also modify the structures rather in-gas. So and next time we are at that time there parameters we are developing some. This size is almost the people are using the 5 micrometer scale and between 10 micrometer scale. Because in this case we use a 10 micron scale. So you can see. Okay. This is our photomix, same image of our photomix. So this is some bias line, and this is in 2 bias line, and this is a broadband antenna. Yeah? So as you can see, some this Taras generated is just in the photoconductive material. You can see some square pattern. This is a photoconductive area. So some this in the photoconductive also we insert the finger into digitized patterns for increased efficiency. So this is just around the 12 micrometer scales. So. But it's dependent on photon density.